Chapter 5 in our textbook is entitled Thermochemistry. In Chapter 1 of our textbook, which was entitled Matter, Energy, and Measurement, we got the understanding that energy is the ability or the capacity to do work or transfer heat. Now, while we did not talk at length about energy in Chapter 1, I felt that it was most beneficial to defer that conversation until we got to Chapter 5. This chapter is all about thermodynamics. Thermodynamics, by definition, is the study of energy and its transformations. But our discussion specifically is going to deal with a subset or a subheading of thermodynamics, one that we call thermochemistry, in which we study the nature of chemical reactions and the energy changes that are associated with these reactions. Now, it's important that we do not confuse heat with energy, energy with temperature. While these concepts are similar, they are tied together. They are not one and the same. So when we talk about temperature, when we talk about energy, there are units of temperature, but there are also units of energy. Some of the standard units of energy are the British thermal unit, the calorie, the food calorie, and the joule. Now, it's important to note that a calorie is different than a calorie. And I know that if you're just listening to that, that may not seem to make a whole lot of sense, but I'll elaborate in just a moment. The British thermal unit, by definition, is the amount of energy required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So if you have a pound of water at 75 degrees Fahrenheit and you want to increase the temperature of that water by 1 degree Fahrenheit, then you would have to put in 1 British thermal unit's worth of energy. A calorie has a similar definition. A calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Now, typically, we think of the unit of calorie as it is associated with foods or beverages, the caloric value that a food or beverage is said to possess. Now, that calorie is a different calorie. That's what we call a food calorie, a capital C calorie, if you will. And that calorie is 1,000 little c calories. I'll say that again. 1 big C calorie, or a food calorie, is the same as 1,000 little c calories. The prefix for 1,000 is kilo, so a big C calorie is also the same as a kilocalorie. Now, with that being said, the standard unit of energy in the SI system is the joule. Now, the joule is such a small unit. Oftentimes, we will see energies, specifically with chemical reactions in mind, referenced in kilojoules. When considering the energy associated with a chemical reaction, we need to understand and focus on the reaction at hand. In doing so, we have to isolate a portion of the universe that we're going to study. We define that as the system. An example of a system might be a beaker of water in which a chemical reaction is to take place. That is the area or the portion of the universe that we are going to study. Everything else in the universe is considered to be the surroundings. So the universe is made up of the system and the surroundings. Now, as we define the system as the area of the universe that we are studying, we need to understand that there are three different types of systems. There are open systems, there are closed systems, and there are isolated systems. The differences between the three lie in what can be exchanged back and forth between the system and the surroundings. In an open system, both energy and matter can be exchanged between system and surroundings. Once again, if we consider a beaker of water in which a chemical reaction is to take place, we can put matter into the beaker, we can take matter out of the beaker. We can heat the beaker up, we can cool the beaker down. So both matter and energy can be exchanged between the system and the surroundings. In the case of a closed system, we see a region where only energy can be exchanged between the system and the surroundings. No matter can be exchanged in a closed system. Imagine if you had a mason jar, and inside that mason jar there was a chemical reaction taking place. No matter can get in or out of the jar if the lid is sealed, but you can still heat it up. You can still cool it down. So energy can be exchanged, but not matter. Lastly, an isolated system is one in which neither energy nor matter can be exchanged between system and surroundings. An approximation of an isolated system would be a thermos bottle. If you imagine the workings of a thermos are such that matter can't get in or out once you close it. Also, energy is limited. Energy cannot get in or out. If you have some hot soup in a thermos, that soup is going to remain hot because energy is not going to leave the system to the surroundings. If inside the thermos you have a cold Mountain Dew, then the surroundings can't let energy into the system to warm up the Mountain Dew. It keeps your hot soup hot and your cold Mountain Dew cold. It is an isolated system. When we talk about the energy associated with a particular process, quantifying that energy is going to have three parts. It's going to have a number, it's going to have a unit, and it's going to have a sign. Now, that's no different than any other measurement that we've taken, other than the idea of the sign. You'll note that I've gone on record as saying that numbers without units are meaningless in measurement. So the number and the unit shouldn't be news to us. But the idea of a positive or negative sign associated with thermodynamic quantities may be something new to us. Well, the understanding is that if the energy value is positive, that means that energy goes into the system from the surroundings. If the energy value is negative, that means that the energy transfers from the system to the surroundings. If energy is transferred to the system from the surroundings by means of heating, the process is said to be endothermic. Here on this slide, we see the reaction of ammonium thiocyanate and barium hydroxide octahydrate. These two compounds react in order to form barium thiocyanate, ammonia, and water. From a thermochemical point of view, it's important to note that upon the formation of these products, we see the heat flow from the surroundings into the system. The temperature of the surroundings drops because the energy from the surroundings has now gone into the system. When energy is transferred from the surroundings to the system, the process is endothermic. But when energy is transferred from the system into the surroundings, the process is said to be exothermic. Energy is exiting the system. Here we see the reaction of an alkali metal, potassium, with water. Many chemical and physical changes that occur around us, especially in a laboratory setting, occur under the essentially constant pressure of the Earth's atmosphere. If a process does take place at constant pressure, then we can account for the energy transfer via heating by measuring the enthalpy of the system. For a constant pressure process, enthalpy is essentially the heat associated with a process. Here we see the thermochemical equations associated with both an endothermic reaction and an exothermic reaction. A thermochemical equation not only speaks to the products and reactants in a reaction, but also the energetics, whether energy is required or energy is released. The first reaction listed speaks to the combustion of propane. The energy value associated with it is a negative 2252 kilojoules, which means that for every 1 mole of propane that undergoes combustion, we see nearly 2300 kilojoules worth of energy released by the system into the surroundings. The second equation deals with the reaction of glucose with water in order to form hydrogen gas and carbon dioxide. That process requires 627 kilojoules worth of energy. So while the combustion reaction is an exothermic reaction, the bottom reaction is an endothermic reaction. So summarizing the concepts of endothermic and exothermic. When we have a process with a positive value of delta H, that is the change in enthalpy, that process is endothermic. A negative delta H for a process is exothermic. Now we deal with delta H, which is the change in enthalpy, which again is essentially the heat that is being transferred from the system to the surroundings or from the surroundings to the system, depending upon the endothermicity or exothermicity of a process. If a process is indeed exothermic, then the reverse process would be endothermic. For example, if we looked at the combination of carbon dioxide and water in order to form propane and oxygen, the reverse of the combustion reaction on the previous slide, that process would be endothermic. That process would require 2252 kilojoules worth of energy. We're not concerned with the exact enthalpy of products and reactants. Instead, we're concerned with the change in enthalpy. It's that change in enthalpy that is equated to the heat or the thermal energy that is transferred in a given process. So we can measure that delta H through calorimetry. The device used to measure heat flow is simply known as a calorimeter. And we can approximate a calorimeter by using a double coffee cup scenario. If you had a glass of hot water, literally a glass of hot water, the thermal energy from the water would be transferred through the glass into your hand. So you would lose some of the thermal energy in the water to the surroundings, which would be your hand. If you instead placed that hot water in a coffee cup, then you wouldn't feel that thermal energy because, well, styrofoam doesn't conduct heat very well. If you were to place that coffee cup inside another coffee cup, now we have a system where we can optimally measure the energy that is transferred based on a given process that takes place within. We don't have to worry about heat loss to the surroundings unless, of course, we are measuring specifically that heat loss. By transferring thermal energy in a given process, we're going to see a temperature change in the system. It should be noted that different substances respond to being heated in different ways. Some substances will show that increased energy as a temperature change, while some of them will store that thermal energy more readily. Enter the idea of heat capacity, or the ability of a substance to store thermal energy. More scientific definition speaks to the heat capacity as the amount of energy required to raise the temperature of 1 gram of substance by 1 degree Celsius, or by 1 Kelvin. It should be noted that the unit of the degree Celsius, the incremental unit, is the same as the incremental Kelvin. If the substance in question is 1 gram of substance, then we refer to the specific heat capacity. If the amount in question is 1 mole of substance, then we refer to the molar heat capacity. So we look at various substances, whether they be elements or compounds, and we can compare their ability to store thermal energy. How much energy is required in order to see a temperature change of 1 degree Celsius or an increase of 1 Kelvin? If we look at the substances, calcium carbonate has a specific heat capacity of 0.82 joules per gram times Kelvin. That means that in order to induce a temperature change of 1 Kelvin, 0.82 joules worth of energy are required to raise the temperature of 1 gram of substance by that amount. Carbon dioxide similarly requires 0.84 joules worth of energy to raise the temperature of 1 gram of substance by 1 degree Celsius or 1 Kelvin. Liquid water, on the other hand, has a significantly higher specific heat capacity. It's nearly 5 times that of carbon dioxide. In order to induce a change in temperature of 1 degree Celsius or 1 Kelvin, we have to put in 4.18 joules worth of energy. We can measure that delta H value indirectly if we carry out a reaction in aqueous solution in our double coffee cup calorimeter. The heat change by the system can be found essentially by measuring the heat change for the water in the calorimeter. In this instance, we're going to treat the water as the surroundings, but what's happening inside the water is the system. It's very important that we understand the difference between the system and the surroundings. So when the temperature of the water goes up, that means that energy is being released by the system into the surroundings, which include the water. So by measuring the temperature of the water, we're measuring the temperature of the surroundings. Now, the specific heat for water, as we saw in the previous slide, was 4.18 joules per gram times Kelvin. For dilute solutions that are not very concentrated, then we can treat the specific heat of such a solution as that of water. From there, we can calculate delta H, which again is equated to Q by understanding that the heat transferred in a given process is related to three factors: the mass of the substance being heated, the specific heat of the substance or how the substance responds to being heated, as well as the temperature change associated with the reaction. So if we measure those values for the solution, which are the surroundings, then we understand the amount of heat that is transferred to the surroundings or from the surroundings. Energy that is being transferred to the surroundings has to come from the system. Energy that is transferred to the system has to come from the surroundings. So those two energy values are equal in number but opposite in sign. If 500 kilojoules worth of energy leave the system, that means that 500 kilojoules worth of energy are absorbed by the surroundings. So one of those values would be a positive 500 kilojoules. The other would be a negative 500 kilojoules. We're going to end our discussion of Chapter 5 with a focus on bond enthalpy. Bond enthalpy is the change in enthalpy associated with breaking a particular type of bond in 1 mole of a given gaseous substance. At the top, we see what is essentially a chlorine molecule, 2 atoms of chlorine covalently bonded together. Remember, nonmetals are bonded to one another covalently. So if we were to break that bond, if we were to disrupt that interaction, we would have to put a certain amount of energy into that system. On the bottom, we see what can be approximated as a methane molecule, methane having the molecular formula of CH4. The black ball at the center represents a carbon atom, and it is bonded to 4 hydrogen atoms. In order to break all 4 of those carbon-hydrogen bonds, a certain amount of energy must be put into the system. Think about it as a game of Red Rover. If you are joining hands, the strength of that interaction can only be tested by somebody coming and trying to break through. The amount of energy that is required to break through those hands is essentially the bond enthalpy. 3 things that we should take note of with regards to bond enthalpy. The bond enthalpy is always positive because energy is required to break bonds. Energy is released when new bonds are formed. So the bond enthalpy associated with breaking bonds is going to be positive. But in forming new bonds, that is going to be an exothermic process. The energy value is going to be negative. And the greater the bond enthalpy, the stronger the bond. In other words, the more energy that is required to break that bond. Here we see a table of average bond enthalpies. The first enthalpy listed is that of a carbon-hydrogen single bond, one of the bonds that we would see in a molecule of methane. In order to break a mole of carbon-hydrogen single bonds, 413 kilojoules worth of energy are required. So since on the previous slide we saw 4 different carbon-hydrogen bonds that needed to be broken, taking 4 times that 413 gives us 1652 kilojoules worth of energy. So in order to break up a molecule of methane into an atom of carbon and 4 atoms of hydrogen that aren't bonded to one another, it requires over 1600 kilojoules worth of energy. Now, when new bonds are formed, we see the release of that much energy. So if carbon and hydrogen were to combine, we would see the releasing of 413 kilojoules worth of energy. Directly next to it on the table, we see nitrogen-hydrogen in the form of a single bond. In order to break that bond, we see 391 kilojoules worth of energy are required. The next table over, or rather, excuse me, the next column over, we see an oxygen-hydrogen bond at 463 kilojoules per mole, an oxygen-oxygen single bond at 146 kilojoules per mole, and an oxygen-oxygen double bond. Note the two lines between the two atoms of oxygen. Those two lines speak to more electrons gluing these two atoms together. And since there are more electrons, then we are going to see an increase in bond enthalpy. In other words, an oxygen-oxygen double bond is going to be stronger than an oxygen-oxygen single bond. It will require more energy in order to break an oxygen-oxygen double bond than an oxygen-oxygen single bond. Well, that, ladies and gentlemen, essentially wraps up our discussion of Chapter 5, everything that thermochemistry has to offer. Take care. Have a wonderful day. Enjoy.